So, so this work is inspired by, sorry, first of all, I'm very happy to be here. Thanks for inviting me. This work is inspired by the following societal problem, which is participatory democracy. And the idea here is that it's a process emphasizing the role of citizen involvement in political decision making. So instead of making decisions in a small committee, could you possibly make decisions at scale? Could you make decisions in groups of 100, 1,000, a million, or a billion, right? And the technical problem, which corresponds to the societal problem, is decision making at scale. So you could imagine decision making at scale as being primarily voting. So for example, you could have a simple poll could be, you could ask Obama or Romney, right? And you vote for one or the other. An example of a more complex process, a more complex decision that you might want to make is something like, how can we cut the US budget deficit? And if you pose this problem on any bulletin board, on any public bulletin board, what's going to happen is that there's like, some guy's going to say, well, you guys are all communists, someone is going to call you a bloody capitalist, and then some people are going to just sort of smile, retweet, and nothing's actually going to happen, right? And so the question is, can you design algorithms, mechanisms, and platforms for essentially being able to get a coherent answer to questions of this type from a reasonably well-informed crowd? So how can we make decisions at scale in the face of polarization and extreme opinions? And the problem, of course, is that free-form discussion boards often degenerate into vitriol. One person says something really extreme, and then that's where the conversation heads. Yeah. So what we need is not just free-form discussion boards. What we need are more structured modes of interaction with some provable properties. And so just to show how badly we are polarized, right? There isn't even agreement on whether we are polarized or not. There's a sort of big set of results which says that we are highly polarized. There's also another set of results which says we are not really polarized, right? There's a third set of people who actually think that polarization is good. So our solution of this problem, right, is to be a bit of an ostrich, which is let's not actually worry about whether there's polarization. That's also our societal decision about this problem, to be a bit of an ostrich. But also our personal decision about this problem is to be a bit of an ostrich with a head in the sand, which is we're not going to try to understand whether polarization happens, why it happens, right? So our goal is not to sort of do science, but to do engineering. So we want to design systems and algorithms which are going to lead to decisions, and not worry about whether society is getting polarized or not polarized. So here are some high-level design goals. So when you do something like participatory democracy, the way is different from voting, is that the number of candidates is equal to the number of voters. So you can essentially assume that everyone has an opinion. You need to aggregate everyone's opinions. Right? No voter can look at all candidates, again, at scale. And so that necessarily forces you to have small group interactions. And a small group interaction could be something as simple as you're shown two opinions, and you are asked to choose between one of the two, right? So for example, it's similar to what Sigal was talking about. You're given two candidates, and you choose between one of the two candidates. And you want to limit cognitive load that you impose on anyone user at any given time, right? Because people can't keep all these different candidates in mind. We want to support not just voting, but also things like interaction, collaboration, and discussion. And you want to align incentives. So these are the high-level design goals. And the complexity parameter that we want to look at for small group interactions. When we say we need small group interactions, one natural complexity parameter is group size. And that's the one that I'm going to focus on now. How big or small does a group need to be in some stylized settings to be able to come to a decision? And so today I'm going to talk about this method called Triadic consensus. This is somewhat stylized. It's going to be a non-axiomatic framework in the sense that I'm going to describe an algorithm. I'm not going to describe the axioms that we're trying to satisfy. And the reason for that is I don't get the sense that we understand the design space enough to lay out a bunch of axioms and say we want a decision-making process that has these axioms. And if there's time remaining at the end, I'm going to describe two very other different kinds of designs, which also try to solve the same broad problem. And that would illustrate that at least I don't think we are at a point where we're going to lay down three axioms and say we want a system that satisfies these three axioms. And in a later workshop, the AGT practice workshop, I'm going to talk about non-stylized systems. I'm going to talk about systems that we actually built and deployed and which are being used in dozens of cities right now to do some form of participatory democracy. And also describe sort of broader research directions and design philosophy. But today I'm going to focus on this stylized model. And so the stylized model came from this very simple experiment that we did several years ago, where we got a bunch of people, we asked them to self-identify as Republicans or Democrats. We asked them to make budgets, and then we divide them into groups of 3, and each group had either 2 Democrats and 1 Republican, or 2 Republicans and 1 Democrat. And in each group, we asked each member to choose among the other 2 budgets. So A would be asked to choose among B and C, B would be asked to choose among A and C, C would be asked to choose among A and B. And what we realized was that the winners of these tended to be, just from our observation, they tend to be very reasonable budgets. They tend to be very non-partisan. So what happened, at least in that small-scale experiment, that in a majority of the groups, the minority actually won. So both Republicans voted for the Democrat, or both Democrats voted for the Republican. And that's not a formal argument of any type. It's just what sort of made us think that perhaps this kind of triadic voting is something which is interesting. So what we're going to try to get towards is the median of a group of opinions. So the famous example for this is that Sir Francis Galton went at some village, asked people to guess the weight of an ox, and it turned out the median of the weights was actually a very good approximation. The median of the guesses was a very good approximation of the real weight of the ox. And since that time, people have typically thought of the median of a set of opinions as somehow the consensus voice. So again, like I said, today we are doing something stylized. So our goal would be to try to extract the median of a group of opinions. And so there's also a median voter theorem which says that if you're going to actually choose the median of a bunch of values, then reporting true values is incentive compatible. So the question that we're going to ask is, if you have something a bit more complex than values on a line. For example, if the question you want to ask is, what's the ideal way to regulate off-road traffic? Or if you want to aggregate unstructured, so for example, if you want to aggregate some unstructured estimates where it's not even clear to you as a system designer how to take the median of a bunch of reported values, or where there's no consistent vocabulary for a voter to express a position, then what do you do, right? So in the weight of an ox, everyone sort of reports in the unit of kilograms. But what if we ask you something like, if we're asking you about more parking enforcement versus less parking enforcement in Berkeley, right? Is there sort of a consistent unit that everyone's going to report? And what if these values are not one-dimensional? They lie in some more complex space, which as a mechanism designer, you don't actually understand. So, but quite often, even though you might not understand the underlying space, the median is still well defined. You can define the median in general for a general space as just the point that minimizes the distance to the ideal positions of all the voters. And this is related to the Condorcet winner in some very interesting ways. So is the problem clear? Our goal is to extract the median vote of a bunch of voters, right? But we might not have a consistent vocabulary in which they'll express their preferences. Right? So there's no way for them to describe that my vote is the point 2, 3, 4 in this 3-dimensional space.
But distances are somehow able to be discussed.
So there exists some space. And so in fact, I didn't mention it because it'll take a long time to describe it. For example, Eliot has a paper which does a very nice job of this. You assume that there's some underlying space, but nobody can articulate what that space is, right? But it exists, and people sort of report. So people can sort of do simple computations on that space. So for example, you can make out whether in this space something is closer to you than something else, right? But you can't. You have no common vocabulary for either expressing that space or expressing distance in that space.
Right, so I just wanted to ask what can be talked about, and I guess you'll get to that.
Sorry?
What can be talked about, and you'll get to that, right?
So you can express your own position. So there's some way in which you can say what your position is. You just can't situate it. You just can't situate it in this underlying space. So of course, in this model, you can expect people to compare proposals. So for example, in the previous talk, every voter was being able to ask to compare 2 candidates. But you could perhaps do more. perhaps you could ask questions like which proposal is closest to X and sort of between Y and Z. Okay? And the question is, if you're given primitives of this form where people still can't quite articulate where they are in a space, but they can answer questions of this type, then given more detailed questions that people can ask, can you do more detailed computations like extracting the median? So we want to identify a magic box, and a magic box is some calculation that a user can do, and see if we can use that magic box to derive, to actually get median estimates from a crowd. So one simple thing that you could say is, suppose we are given the following primitive. Suppose given 3 people, we could identify their one median. Right? So 3 individuals can together figure out what their one median is. So let's assume that we are given this box, and let's see what we could do. So let's think of the following cartoon game. Okay? Let's assume that all individuals are in this some complicated metric space. Let's say this tree represents the metric space from which individual opinions are drawn. We have a box. We take all the participants. We put them in a box. We take them 3 at a time. So we draw 3 participants at random from this box. Now these 3 participants correspond to these 3 positions in the underlying metric space, and they can somehow magically compute their one median and report it back to you. So these 3 participants can figure out that their one median in this underlying space happens to be this yellow opinion. This yellow opinion happens to correspond to one of the participants, and so essentially this opinion or this participant is essentially the winner of this triadic election. Now, of course, for the simple case of where participants lie on a line, this median opinion would just be one of the 3 participants. In fact, it would be the middle of the 3 participants. And so what you do is you take this winner and you remove all 3 of these participants from your box, and you add 3 copies of the same participant back to the box. And what that means is, in your box, and the next time you draw a random sample from this box, this yellow participant is 4 times as likely to be drawn as any other participant. Yes?
Which 3 did you remove?
You remove the 3 that you had drawn. So you draw 3 uniformly at random. You take their median. You remove the 3 that you already drawn, and you add 3 additional copies of the yellow guy back to this box.
The yellow is one of the 3, right?
So if these points happen to lie on a line, then the yellow would be one of. If you assume that the underlying metric space is a line, then this yellow guy would be one of the 3 participants. Right? But if it's not on a line, then this may not be one of the 3 participants. And so somehow this is easiest to understand this mechanism on the line. So perhaps I should just restricted myself to the line, but the line is a bit too stylized. So now we have 4 yellow guys in this box. We again draw 3 more, and these are the 3 that we end up drawing. In this case, the median actually happens to be the blue point, one of the participants. So we'll add 3 copies of the blue guy, and now we have 3 yellow, 3 blue, 1 white, and 1 brown. We keep repeating this process, and the winner is the remaining.
What happens if the median is not one of the colors in the box?
Then this whole approach is going to sort of not work.
So what you have in mind is...
No, sorry. If the median is not one of the colors in the box, that's okay. The problem is if the median is a non-participant.
Sorry, yeah, it's a non-part.
Then this approach is not going to work.
So if I was to think about this, what you have in mind is I pick up 3 people, I find that their median consensus is one of the people in the box. Then
yeah.
I'm oversampling that guy, so then I can ask that guy to give his preferences over some complicated space.
That's exactly right. Right. And so there's a big assumption here, and the big assumption is there are 2 big assumptions here. One big assumption is that people can actually compute their medians, and another big assumption is that that median, whatever they compute, is going to be one of the participants in this election, right?
And this voting procedure where you make more of that guy and you bring it over, where are you getting these copies?
So since all we are using these copies is for sampling, making a copy of an individual is just increasing their sampling weight. So, yes.
So what happens if they pick out one of their three opinions, but the one that minimizes the sum of the distances? So that's like an approximate median. Does it still work out? And
so I think that's the one that we want to really prove properties about. So I think that will sort of address all the issues that are being brought up. If you could say instead of, if you could say the following, if you could say instead of finding the one median of these three individuals, right? If you could say A, you vote among B and C, B, you vote among A and C, C, you vote among A and B. If one of you happens to receive 2 votes, then we add 3 copies of that person to the box. Otherwise, if the 3 of you can't agree among yourselves, then there's no way you're going to help my decision-making process. I'm going to kick all 3 of you out. That's the one. If we were to deploy something, that's the one that we would actually deploy. And the small scale experiment that I described, that's what we actually did. So like if a group gets deadlocked, then we just say like, we'll ignore you. And if in a group a winner emerges, then we put them in. Now, but like I said, today we're going to talk about something stylized. I can't actually prove any theorems about this. So the one that you articulate will address all these questions, because then you won't have to worry about, is this space fully populated? And then it'll also answer this question which I had, which is how will these 3 people find their own median? Because right now to find their own median, they have to know the entire space. But if you're just voting among the other 2, then you just sit down in a small group and you talk. But the nice thing is that if you assume that your voters lie on a line, then the 2 approaches coincide. Because then the median of any 3 is going to just be the median, just going to be one of them. So at some point, everything will become one color, and you can say the winner is that color. Or you could, after some point, you'll have mostly 2 colors remaining, or there'll be some colors which will dominate, and you can say the winner, this is the distribution that I get. So just to ask, can someone guess what would happen if we ran this process on this tree? Right? Let's say there's a tree of height 1 million, and can someone guess, like with high probability, will we choose the winner among the top 500,000, right? Which would give you like a square root, which would be like you're saying you're choosing one of the top square root and guys. This top guy is clearly the median. Or it'll be like 1,000, which is the square root of the height, or 20, which is the log of the height, or 2. What would?
I'm not understanding the question.
Suppose I would run that process on this tree.
And what is H? The number of
H is the height of the tree. And the question is, where do you think with high probability, where do you think the winner would come from? 2, yeah. I mean, I wouldn't have asked the question otherwise. The winner would indeed come. So with high probability, it doesn't actually matter what the height of the tree is. With high probability, if you repeat this process, the winner of this simple dynamic, right, would be one of the top 2 guys in the tree. Yeah. Yes?
I don't understand the effect of the network structure very well. I guess I don't see how it's...
So this is, yeah, sorry, I should have clarified. There's no network. So voter opinions are coming from some underlying space. Yeah. And so imagine that there's a metric space which underlies there's an underlying metric space. Every voter's opinion is a point in this metric space. And in this case, what I'm saying is that the metric space happens to form a binary tree. So the distance between this opinion and this opinion is 2. Between this opinion and this opinion is also 2. Between this and this is 1, 2, 3, 4, 5. So this binary tree is not a social network in the sense of somebody knowing somebody else. It's sort of the metric space which tells me the distance between 2 opinions.
Sorry, so the definition of the median in this case is the node that's closest to halfway between the shortest path connecting 2 nodes?
So for 2 nodes, the median may not be very well defined. For 2 nodes, the median could be anyone which is, for 2 nodes, the median could be anyone along the shortest path.
What is the definition of the median?
So for 3,
If you write the 3G, then there's a center that's going to be.
Yeah, thanks. It's exactly what Eva said. For 3 points, the median is well defined. For 3 points, the median would be exactly the point where they diverge. So you take the short, if you look at these 3 points, so of course the definition of the median, the exact structure would differ from problem to problem. But in this case, if I would take this guy, and this guy, then this would be the median. Because this pink guy lies on the shortest path from the blue to the black, lies on the shortest path from the blue to the brown, and lies on the shortest path from this green to the any of them. Okay. So in this particular case, in the tree case, the median is exactly what Eva said. In general, the median is just whichever point happens to minimize the sum of the distances to your 3 chosen participants.
Sorry, what's the meaning of that statement that you asked us about? So winner is chosen from the top D levels.
With high probability.
How many iterations?
So let's the final one. Let's keep running it till we have one winner, and then I'm of course hit the complexity. I hit the. Yeah. So if you have a square grid of size like 1,000,001 times 1,000,001, right? So you have like a big grid with a trillion nodes. Then with high probability, with 99% probability, the winner will come from the central 3 by 3 grid. Right, so essentially, this very simple process sounds like it couldn't possibly lead to very good results. But if you run it, at least for these stylized cases of a tree and a grid, it finds you something which is almost exactly the median. And so here's the basic proof argument. So again, I'm not going to give a full proof, but I'm going to at least give intuition for the tree case. Okay? So what happens in the tree case is, imagine that. So in fact, for the tree case, to understand what happens in the tree case, let's just focus on one edge. Okay? Suppose we focus on just this one edge. Okay? Then let's color everybody who's on one side of this edge red and everyone who's on the other side of the edge blue. Okay? Then we pick, and then let's write down the number of blue points we have on a line. So right now we have 3 blue points. So we say that we at this point with this coloring corresponds to point number 3. Then let's draw a sample of size 3 from this set, right? There are 3 red points. So we choose a red point with probability 3/8 and a blue point with probability 5/8. We draw 3 samples. The median of these 3 samples happens to be this individual. So now we're going to throw away the 3 samples that we had already chosen, and we're going to add 3 copies of this individual who's blue. So we're going to now have 2 blue points and 2 red points and 6 blue points. So we move from the point 3 to the point 2. In general, at any given time, we are going to, so at any given point, it's easy to see that if we are at point 4, we can either remain at point 4. For example, if we draw all 3 red or all 3 blue, we'll remain where we are. Or whichever we draw less of, that number is going to go down by 1. So we're essentially doing a random walk on this line. And the reason that, as far as this edge is concerned, all that matters is whether a point is blue or red. If 2 points happen to be on this side of the line, then the median will be on this side of the line. If you have 2 red points, then the median will be on that side of the line. And then this ends up being a fairly simple recursion to write. If you're at point I, right, then you're going to move to point I plus 1, precisely if you draw exactly 2 red and 1 blue, and that's going to happen with probability I over n squared times n minus I over n. I'll ignore this factor 3. And if you end up drawing 1 blue and 2 red, then you're going to move right. So now you have this fairly simple Markov chain which is describing what's happening on a tree. And then sort of given this very simple Markov chain, you can write down the probability that the winner is going to be red, given any number of initial red people, and then also you can analyze the time to absorption. We're going to have all blue or all red. And so this probably that whether red wins given given the initial point that you start, is actually the one that gives you the fact that I mentioned before, that the winner is going to be on the top 2 levels. Okay? And by analyzing the absorption time of this Markov chain, you can actually say that the time to absorption is going to be n log n, which is the question that Eva was implicitly asking.
Levels you mean by high probability and expectation?
With high probability. But the probability is, yeah, with high probability. But the probability, at least for the tree case, is so high that it's not even worth writing. Because what happens for the tree is that basically you want to understand what's the probability that this tree wins. But this tree, if you think of this tree as being red, this tree has only n over 4 elements. So it's going to win with almost minuscule probability. The same with this, the same for this, and the same for this. So with very high probability, you're going to be in one of the 3. Yeah. Sorry, did you have a question? Oh, 5 minutes. So in general, this is easy to believe. The same thing. You can use the same method for the grid. I'll skip this. So in general, it seems like for the line it makes sense, for the tree it makes sense, it might make sense for the grid. But in fact, it makes sense for a slightly larger class of graphs. For any median graph, and a median graph is any graph where every 3 nodes have a unique median. So in a tree, somehow I skipped over why there's a unique median, but in a tree, any 3 nodes have a unique median. So in any graph where every 3 nodes have a unique median, triadic consensus finds a 1 plus order square root log n over n approximation to the 1 median in order n log n rounds. And so is this a reasonable thing? Right? So we said suppose that triads could find their 1 median. Right? Is it a reasonable thing? Can we actually expect these triads to find their 1 median? Or is there a simpler primitive that we could ask them to implement? So that simpler primitive could lead to a 1 median. And the simpler primitive actually, so first of all, first of all, 1 median is already somewhat reasonable, because for triads in median, if you have a median graph, then the 1 median is the same as the Condorcet winner for these three participants. And then of course, when voters lie on a line, then the 1 median is just the middle voter in the triad. But you also have a box. You can also replace this by a simpler problem. And you can also say, if a voter can answer the following question, what proposal is closest to x being me, and between y and z? And if a voter can answer this simpler question as opposed to finding the full median. If anyone is interested, there's a very interesting lecture at Stanford tomorrow. So I'm going to skip the details, but if you can get individuals to answer questions of this type, which proposal is closest to me, and between y and z, then you can use that as the magic box to then construct a 1 median magic box. I'm going to skip details of exactly how you do it. But basically what happens is you have a chooser and 2 proposers. The proposers take turns proposing a solution, and the chooser either says, okay, I like it better, and accepts it, or says, no, I don't like the one that you now propose, and rejects it, in which case whatever was accepted last becomes the winner. Okay, I know I went through it very fast, so I don't actually expect you to get the details of this side. But I want to mention, but I said somewhere here that this is, in this case, for everyone to participate truthfully, for every triad to truthfully find the 1 median, is a Nash equilibrium. And I want to just, instead of giving details of the proof, I want to explain what I mean by Nash equilibrium. So I'm going to assume that participants are not strategic in declaring their positions. So the positions that the participants declare are non-strategic. They're just truthful by fiat. Okay? But the strategy space is not what positions they declare, but the votes that they cast in any triadic interaction. And then if we assume that, then we can show that truthful voting is a Nash equilibrium in the entire extensive form game over the entire n log n steps. Okay? And this assumption may be too strong, right? That participants are not strategic in declaring positions. So the assumption is too strong, then there are 2 ways of thinking of this. One is, can you think of designing the right mechanism? Right? Think of that as an open problem. Right? So don't think of what we did as a result. Think of it as an open problem. Right? Or you can just interpret this result only as an analysis of the dynamics with truthful voters. And just leave strategic issues aside altogether. So at the beginning I mentioned that the one complexity parameter of interest here is the size of the group. And so the natural question is, well, we can do something with triads. Can we do something with just 2 people at a time? Can we have group sizes of 2, ask these 2 people to engage in some interaction, aggregate their opinions, and still find a good approximation of the median? And as it turns out, so could you have a magic box where you put people 2 at a time, replace them with something else, and then ultimately hope to get to the median? And that turns out to be impossible. So no reasonable pairwise magic box or no reasonable pairwise aggregation function can find an approximate 1 median even in median graphs. And this sort of the way to think about this is that when you have 3 individuals, they provide an anchoring effect. So if the 3 individuals, right, then me as a participant can somehow, I can say that person is extreme because I don't like him or her, and this other person also doesn't like him or her. With 2 individuals, there's no anchoring effect. So it's not surprising, but as it turns out, there's a very simple notion of local consistency, which says that if given any group, if the groups look internally the same, then the outcome has to be the same. You can show that no 2% locally consistent reduction can approximate the median up to anywhere like 1 plus small o of 1. And the graph that the metric space that shows that counterexample is just this metric space where you have a big star and then a long line hanging off the big star. I think I'm out of time, so I'm going to stop with first the observation that what we talked about today was very stylized, whereas I started with this participatory democracy example. And in the talk on the algorithmic game theory in practice workshop, I'm going to focus more on the deployments that we did as opposed to stylized models. And then some problems here are, can we generalize this past median spaces? So median spaces are very broad. They include trees, grids, hypercubes. They include anything called a reduction of the hypercube, but they're still not as general as all metric spaces. So can we generalize this past metric spaces? Can we use other magic boxes as opposed to triads finding their own median? Can we constrain the winner of a triadic interaction to be a participant in the triad? Okay? And it still proves strong results. So in my mind, that would really make it a practical protocol. Can we have stronger incentive alignment than the one that we showed? Can we do experimental studies of small group consensus? Are there other small group mechanisms which are very different from triadic? And then once we understand the space of this, the design space a little bit better, can we do an axiomatic treatment of the problem? Or is there some sort of more detailed meta model of the problem that we are missing? If we were to write that meta model, then the right algorithm would present itself. So I think, thank you.
So do you know that your algorithm does not work for some graphs?
Well, if it's not a median space, then the notion of a median is not even well defined. Right, so there's no such thing as a median if it's not a median graph. So, because in the sense that given 3 individuals, there may be many medians. And so I don't quite know how to analyze it. So,
median, I might get really bad. That's what you're saying.
So we do know that there exist examples, there exist artificial examples, where if you constrain the winner of the triadic interaction to be a participant in the triad, then we cannot recover the results that we have exactly as they are. So in my mind, so once again, even though I said this before, in my mind, the reason something like this is very attractive is because this does not make any assumptions about is there 1 median, is there 2 medians, are there like many medians, or which median are you picking, and how do you pick the median. So for this specific thing, we do have counterexamples where our results as stated don't hold, but perhaps there's some other way of analyzing this which you are missing.
So you could add arbitrarily small noise to the distances and everything becomes a median space, right? You have a finite metric space. You could have the distances minutely.
No, I mean, unfortunately not. So the kind of thing that you're describing might be very useful in analyzing this protocol where you have to choose one of the 3. But if you're actually trying to find the median, then the problem is that in median graphs, is a graph where every 3 nodes have a unique median. And so, but the way we are using it, right, we are assuming that this median space is fully populated. So you might be able to enforce uniqueness of a median by perturbing the space. But you pick the median, and there's no participant corresponding to the median that you picked. And so that problem you can't solve by perturbing. But you could solve that problem if you constrain the winner of a triadic interaction to be one of the 3 members of the triad. So the fact that whether the median is unique or not, I think is the smaller problem. I think the bigger problem is the median may not even be populated.
What happens if there's noise in the sense that it doesn't move exactly to the median, but maybe?
So I don't quite know how to analyze it for general median graphs. Because for general median graphs, the proof gets very technical because you have to sort of take all sorts of convex cells. But for the simple random walk that I had, that is very robust. So you can move it around. Because also what happens is that walk is very strongly biased towards one direction versus the other. So small noises won't change that particular. So for a tree or for a grid or for a line, it would be very robust.
We're quite a bit over. So let's thank Ashish again.
Thank you.